Okay, this portion of the carboxylic acid unit, I'm going to focus on the different types of carboxylic acids. The ones that we've gone through before have essentially been what we call saturated carboxylic acids, and by saturated, this would be butanoic acid. We mean that the hydrocarbon chain has no double bonds. So you'll see on the next slide, the first type that we're going to talk about is called an unsaturated carboxylic acid, and a common occurrence with these is when we're talking about fatty acids, which will end up making coming together to make triglycerides, which are lipids. If there's a benzene ring, it's referred to as an aromatic acid. We briefly spoke about this already. When you have a hydroxyl group on there, it's referred to as a hydroxy acid. Oftentimes it's on the second carbon, which is an alpha carbon, or sometimes on the third carbon over, which is a beta carbon. Those are commonly used in skincare. Dicarboxylic acids we briefly talked about before as well, and a precursor of some things to come, we have amino acids, which we're going to focus on greatly when we start talking about proteins. So unsaturated acids, again, are commonly referred to when we're talking about fatty acids, and this is one example. Stearic acid is a saturated fatty acid, and it has a melting temperature of 70 degrees Celsius, which means that at room temperature it's going to be a solid. Oleic acid is an unsaturated fatty acid, and with only one double carbon bond, ends up having a much higher melting temperature, so it's typically liquid at room temperature. And these fatty acids are what make up the fats in our bodies, and these stearic acid and oleic acid are referred to as fatty acids. They're long hydrocarbon chains, but the saturated ones have very, very straight structures like this, and they can align themselves in nice, even rows. They're very organized. You can pack them tightly, which makes that organized structure really packed tight, so it tends to be solid at room temperature. As soon as you get a double bond in the unsaturated, in this cis configuration, you end up getting bends in the molecules. So we don't end up with nice straight chains anymore, and they're very curvy, and you can't pack as many of them into the same space as you could compared to saturated. So these tend to be liquid at room temperature because they're less dense. You can't fit as many molecules in one space. So we tend to think of our saturated fats as coming from milk or animal sources. There are some examples of saturated fats, like palm oil have high concentrations of saturated fats, and coconut oil does as well. Those are vegetable sources, but typically we think of saturated fats coming from animal sources. And our vegetable oils are either mono or polyunsaturated fats. Again, this will be a conversation that comes back when we talk about lipids. Aromatic carboxylic acids do have a benzene ring, and the base of the very basic aromatic carboxylic acid is referred to as benzoic acid. And I think for the most part, if we have a group attached, these examples that you see here are toluene. So the benzene with the methyl group we refer to as toluene, and they're calling this orthotoluic acid. So this carboxylic acid group makes this the number 1 carbon, and this would be the number 2 carbon then. I think I personally would prefer just to call this 2-methyl benzoic acid, but according to the fancy schmancy IUPAC people, there has to be a certain way to do things, even though we teach you all of these other common unorthodox ways like ortho and para and meta and alpha and beta hydroxys, and it's very confusing sometimes when all of these things overlap and we still commonly use the old way of doing things in modern times. This is just a bigger picture of the same thing. We briefly talked about dicarboxylic acids before as well, and malonic acid is an example. This one's drawn a little bit differently. So there are 2 types of reactions that can occur with these, and it's called decarboxylation reactions. And the first one, and this next screen has it blown up a little bit bigger. So if we have malonic acid, the way that this was drawn before was we had 1, 2, 3, and we drew it like this before with the OH, that carboxylate group at this end, and then the other carboxylate group at this end. So this is another way to represent it. And in this reaction, it's called decarboxylation because one of the carboxyl groups is being deconstructed, so to speak. So in this reaction at a high temperature, we're losing this COO group, and the product is CO2. So in another reaction, this decarboxylation reaction, this is succinic acid, which is a 4-carbon chain, and it's drawn a little bit differently here. Instead of COOH, like what we have right there, we have this carboxylate group right there. So what happens here is the hydrogen from one of the carboxylate groups combines with the hydroxide from another, and right where these leave, this kind of comes together as a junction, and that HOH becomes water, and we produce this, which is called an anhydride. So this is instead of a dicarboxylic acid, an example of a tricarboxylic acid is the citric acid cycle. And you can see it here. It has 3 carbons. It does have a hydroxyl group right there, but the carboxylate group you can see is on each of those 3 carbons. And I'm really sorry, I've got something itchy in my face, and I keep grabbing my nose because it's really troublesome. I'm sorry if it's distracting. But citric acid is found in fruit juices, but it is also an important component in our body in the citric acid cycle, which we're going to learn is a major component in our metabolic processes. Oxalic acid is one we talked about briefly before, what is another dicarboxylic acid, and it can be found in rhubarb. And it's toxic to us, but it says that 25 grams of oxalate is required to cause death in a 145-pound person. So that would mean you would have to eat about 11 pounds of rhubarb leaves. And I don't know anyone that actually eats the rhubarb leaves, but I think that we shouldn't eat rhubarb leaves. That is the lesson that I can serve you in this. I could possibly be saving your life right now. But even a tinier amount, it's only a fraction that causes it to cause sickness. that causes you to be sick. So the moral of the story is don't eat rhubarb leaves, not even a fraction of the 11 pounds that it may take to kill you. Oxalic acid in the medical field is also used as an anticoagulant, which is an anti-clotting agent. Hydroxy acids are commonly found in skincare products. They do cause the skins to replenish themselves a little faster, so you have regeneration of skin growth, which results in a more youthful appearance. And I'm a firm believer in using hydroxy acids. I think that it makes the skin texture look a little bit nicer. Here is one example is lactic acid, which is actually found in your muscles when you use up a lot of your oxygen stores and your muscles are kind of running in an anaerobic or a low oxygen state. Lactic acid is one of the byproducts. Salicylic acid is a precursor to making aspirin. Both of these alpha hydroxy acids are also found in skincare products. Lactic acid is also found in sour milk, and as I'd mentioned before, muscle tissue from exercise. And salicylic acid was originally discovered in willow bark among ancient. There's evidence of it being used in archaeological ancient civilizations. It was recognized for its pain reducing and fever reducing and anti-inflammatory properties. This is a lady shopping. It's a very blurry image. It's not a blurry lady. It's not your eyes. It's blurry. And she is looking at the ingredients to see if this is an alpha hydroxy product. She's also from Illinois. I don't think I said that right. Illinois. This is an advertisement showing the positive benefits of using alpha hydroxy acids in your skincare product. You can see a youthful, more firm texture in her skin. And I'm not trying to sell the product, but I am telling you I do have personal experience with it, and I think it's pretty nice. Here are two alpha hydroxy acids. These two are actually found commonly as within the beauty products. You can look at labels and see them. So the last one that we're going to talk about with types of carboxylic acids are the amino acids. And the amino acids, all amino acids have this basic structure. I don't really like the way they drew this. The basic structure has a carbon, and attached to the carbon is a hydrogen on this side. This is the way I like to represent it. We have a carboxyl group on this side, and on this side we have an amino group, and it's commonly written as H2N because it is the carbon bonding to the nitrogen. And then this is called an R group, and there are 20 amino acids, and it doesn't matter what amino acid it is. These three things, this, and this, these three components, the carboxylate group, this hydrogen right here, and the amino group are always the same. The only thing different in each of the 20 amino acids is what's attached at this R group. So they are the building blocks of proteins. It says approximately 20 are biologically significant. I don't know what that means. I grew up learning that there are 22, so I'm not really sure on the actual number. I know that in the kits that we use, in which we're going to learn more about amino acids, I'm pretty sure there are 20. This R group does not necessarily represent an alkyl group. We'll learn that there are lots of different variations of what this can actually be. So that concludes my discussion on different types of amino acids. I'm sorry, I screwed that up. I'm going to rewind. Go back. This concludes my discussion on different types of carboxylic acids and some of the applications that they have in our lives. I hope that you enjoyed watching and that you learned something too.